This is a video about unit vectors. Thanks for the PowerPoint, Dr. Bertrand. All right, so you may remember your polar coordinates where you had a certain vector, let's call that vector A, and a certain polar angle. Well, we're not going to be looking at polar angles or polar vectors specifically, but they're important to know in how we translate them into what we call unit vectors. Unit vectors are quantities that specify direction only. They have a magnitude of exactly 1, but what's more important to us is the directions they point in. They point in the x, y, and z directions. So in your notes, make sure you write down that I hat, yes, that's what it's called, I hat points in the x direction, j hat points in the y direction, and k hat points in the z directions. All they are vectors, and they just tell us the direction of that particular physics quantity. All right, so just like we said earlier, in the positive z direction is k hat, in the positive y direction is j hat, and in the positive x direction is I hat. So unit vectors are normally unit vectors have a hat like that, or they're just in bold. So instead of using magnitudes and directions, vectors can be represented by their components combined with their unit vector. So for example, the displacement of 30 meters in the positive x direction added to a displacement of 60 meters in the minus y direction and 40 meters in the positive z direction yields a displacement of 30 I hat minus 60 j hat plus 40 k hat, all in meters. Now, I actually prefer to write it a little differently. In our class, and this is somewhat arbitrary because of the professors that I had, I wrote them like this. So I will actually accept this. 30 I hat meters minus 60 j hat meters plus 40 k hat meters. And if you get the units and the vector backwards, I'm okay with that too. All right, now adding vectors using unit vector notation is actually very, very easy. All we have to do is add the I components together, add the j components together, and add the k components together. Let's do that in this particular example. Consider two vectors. One is a vector, that's 3 I hat plus 7.5 j hat, and b, the b vector, which is negative 5.2 I hat plus 2.40 j hat. And we want to calculate c, the c vector, where the c vector is the a vector plus the b vector. So all we have to do in this particular case is, again, just add up all the i's, all the j's, and the k's. Now you'll notice we have no k's, so let's just focus on the i's and the j's. So we've got 3.00 I hat, and we also, for the other vector, have negative 5.20 I hat. And I can add those two together to just get negative 2.20 I hat. For the j hat part, we had 7.50 j hat, and then 2.40 j hat. Again, I just take those, I add those together, and I get 9.90 j hat. So my c vector would actually be written like this. Negative 2.20 I hat plus 9.90 j hat. Really simple. All right, let's say you move 10 meters north and 6 meters east. You then climb a 3-meter platform and move 1 meter west on the platform. What is your displacement vector? Assume east is in a positive x direction. So this is what we would be doing. Assuming we're starting at the origin, we would go 10 meters north, like that, and then 6 meters east, like that, And then we climb a platform. So we go up 3 meters on this platform. That's kind of hard to draw, but I'm just going to show going up like that. It's not a very good vector, but we go up like that. And then we move 1 meter west. So back sort of in that direction. Okay. To write out the displacement vector, we would look at each of the directions. So in the x direction, we went a +6. We went +6 meters because we said east is in the +6 direction. Then we also went 1 meter west. So that would be -1 in the j hat direction. Oh, I'm sorry, in the I hat direction. So in the x direction, we would get 5 I hat. In the j hat, or in the y direction, we went 10 meters north. So that would be 10 meters in the j hat direction. And we went 3 meters upward, which is in the k hat direction. So we would simply write that as 5 meters I hat plus 10 meters j hat plus 3 meters k hat. And that would be our displacement vector. Really simple. Okay, suppose I need to convert the unit vectors to a magnitude and a direction. So let's say we're given this displacement vector and we want to figure out the direction. Well, it's pretty simple. We just take each coefficient of the I hat, j hat, and k hat, square it, sum them up, and take the square root. So in that particular example that we had, if we were asked how far we are from the starting point, if we were asked to ask the distance from our starting point, we would simply take our original displacement vector that we calculated out, which was this, and take each part of it, take each coefficient of it, and set it equal to r, and take the square root of each, 5 meters squared plus 10 meters squared plus 3 meters squared, and the solution to that would be our distance from our starting point, in this case 11.6 meters. So pretty straightforward. I think this is a review for most of you. All right, now let's look at the position, velocity, and acceleration vectors in multiple dimensions. So in one dimension, we were used to a position of x, a delta x as the displacement, a v as the velocity, and a as the acceleration. In 2 or 3 dimensions, the r vector is our position vector, delta r is our displacement vector, v is our velocity vector, a is our acceleration vector, and in unit vector notation, we would write them out like this. The position vector would be xi hat plus yj hat plus zk hat. The displacement vector would be delta xi hat, delta yj hat, delta zk hat. The components of the velocity would be v sub xi hat, v sub yj hat, v sub zk hat. And finally, the acceleration vector would be axi hat, ayj hat, and azk hat. Pause the video if you need to write all of that down. So let's look at the sample problem. This sample problem says we've got a position of a particle, and it's given by r is equal to 80 plus t minus 40j minus 5t squared k. We want to derive the velocity and acceleration vectors for this particle. So we want to find the velocity vectors. So what we do is we simply take the derivative. So the derivative of 80 plus t would just simply be 2. So that would be 2 I hat. Now our j has a constant in front of it, negative 40. The derivative of constant is just 0, so we don't get anything for j. J is just 0. And the derivative of negative 5t would simply be negative 10t k hat. Oops. K hat. So this would be our velocity vector. It also asks us to solve for the acceleration vector. So in that case, we again need to take the derivative of our velocity vector. So our acceleration would be the derivative of 2I hat. That's a constant, so it goes to 0. Our acceleration, therefore, is just negative 10, because the derivative of negative 10t is just negative 10, and so we get negative 10 k hat. And the question asks, what does this motion look like? So this motion would have constant acceleration, okay, constant acceleration in the negative k direction. So make sure you write that down so you understand the directions of our unit vectors. Okay, and finally, let's say we're given a position function in this form. R is equal to xi plus yj. So this j is kind of missing. Let's make sure we put it there. Oops. Let's make sure we put it there. Okay. With x is equal to t cubed minus 6 and y is equal to 5t minus 3. So really, it's written like this. Let's just substitute in, and we would get r, our position function, as equal to t cubed minus 6 in the I hat direction, plus 5t minus 3 in the j hat direction. All we're doing is we're taking our functions and plugging them into that vector. It wants us to find the velocity. So again, we're going to find the derivative. So the velocity of the I hat direction would be the derivative of t cubed minus 6. The t cubed part becomes 3t squared. Negative 6 is a constant, so I get 3t squared I hat. For the j hat direction, I take the derivative again of 5t minus 3. So I simply get just 5, because minus 3 is a constant, and that just becomes 5j hat. To find the acceleration, I once again take the derivative of my velocity, which is just the acceleration. So the derivative of 3t squared I hat becomes 6t I hat. The derivative of 5j hat becomes 0, because the derivative of that constant is 0, or constant is 0. So these are my velocity and acceleration functions. Now, in this last problem, B says determine the velocity and speed at 2 seconds. So what I would do is I would take the velocity, which I would simply put 2 seconds into. So 3, I'm going to substitute the 2 into t squared. So 3 times 2 squared I hat plus 5j hat. All right, and that would give me a velocity of 4 times 3, or 12, and let's assume that it's in meters per second, 12 meters per second, I hat, plus 5 meters per second, j hat. So that's the velocity. How are we going to find speed? Well, speed is the magnitude. So to find the magnitude, just like before, we're going to put that into our Pythagorean theorem. 12 squared plus 5 squared is equal to about 13 meters per second. So again, the reason we did this is that we were looking for the scalar value of our velocity, or the distance, the speed of this velocity function. And so we had to go to that equation where we take the coefficients, square them, and take the square root. And that's how we got our 13 meters per second. Another way of thinking about it is this, and just in 2 dimensions, I would have gone 12 meters per second and 5 meters per second in that direction, in the j hat direction. Okay, so this was the j hat direction, this was the I hat direction, and we were simply looking for the speed. So this would represent our speed. And that's it. Bring those notes to class.